The first lecture on nonlinear controls for the aircraft system. Let's assume we have a nonlinear system which can be defined as first order ODE form. And for this system, we can design linear controls and nonlinear controls both. Linear controls we have done. So far, we are designing different types of linear control techniques for the system. Let's assume this is the aircraft system. To design the linear controls, the steps we followed is first we found the equilibrium points, and around the equilibrium point we linearize the system, right? Then for this is the condition for small perturbation in the state variable due to the perturbation exist in the system. And also we assume the small perturbation theory to ignore the coupling terms, which are basically part of variable terms. And once we have the linear system, we can design control such that del x equals to 0 as t tends to infinity. And for designing control, we have conditions on conformity and observability. And once these both conditions are fulfilled, then we can design observer, controller. And in controller, we have designed state feedback control, optimal control. We have designed to validate the control. And also we have done a lot of simulations in MATLAB. But in case of linear control synthesis, it will be different. So here we work more on energy of the system. So here we define the energy of the energy contained in the system. And we need to design a controller in such a way that the total energy should be decayed or minimized. And here we're gonna use some energy function, which is basically in terms of the state variable and the system parameters. And we're gonna design some control which help us to minimize that energy. So here the controls, we can come up different type of control like feedback linearization, and also we have Lyapunov-based control, Lyapunov-based control. So how can minimize the total energy of the system? That is nothing but the Lyapunov function. We refer to the Lyapunov function. And to make the Lyapunov function, derivative of the Lyapunov function to be negative, suppose this is the Lyapunov function, and our main goal is this should be 0, p dot. It is equal to 0, or it is minimized. It is the rate of change of the v is negative. So it means the energy is decreasing. So if you come up some function like this, and if you come up some conditions in such a way that this is fulfilled, then we can design the Lyapunov-based control. And also we can design feedback linearization, and also we have the sliding mode control, backstepping control, and also we're gonna study adaptive control. If any of the parameter in the system is adaptive, if it is time varying, changes the time, and how can design some adaptive control to tackle those kind of situation. But this is also we are going to cover in this content of this course. Now, next question is why we have to study nonlinear controls over linear controls. So as you know, the all practical systems are nonlinear in nature. So once you are designing linear controls, we are ignoring some terms. But practically the system contains a lot of nonlinear terms. That is one reason we have to study the nonlinear controls. And dynamics of the linear system are not well established enough to describe many commonly practical world problems. So that is another reason we have to study the nonlinear controls. In linear system, the system stability depends on the system parameter. Suppose this is our system equation, which is defined in linear form. And the stability can be defined based on the eigenvalues of the A matrix. So the terms actually inside the A matrix actually contain the system parameters. So if the system parameters changes, the eigenvalues also change. So we define the stability of the system based on the eigenvalues of the system. But linear system. But in the case of nonlinear system, the stability depends on the initial condition, input signal, and also system parameters. And also another reason is due to the existence of the discontinuous function like backlash, dead zone, etc. The nonlinear system may not allow linear approximation. But for the starting of linear synthesis, control synthesis, we assume the linear system are assumed to be linearized. This is the condition we do. And based on that, we design the control synthesis. These are the reasons why you have to study the linear and nonlinear controls over the linear controls. It is preferred actually, preferred. Now, let's take an example of the aircraft dynamics, the original equation of motion, translational motion and rotational motion. Let me rewrite the equation what we had before. So we have the equations, aircraft equations. So we have u dot equal to v minus uw plus fx divided by m minus g sine theta, and v dot equal to vw minus ru plus fy divided by m plus g sine phi and cos theta, and w dot equal to u minus pv plus fc divided by m plus z cos phi cos theta. So this equation, we can say this is basically translational. And if you write that rotational dynamics, we have P dot equal to Iy minus Ig divided by Ix Qr plus control Ix. This is, you can assume that total torque exists in the system. It may contain the control torque and also disturbing torque. And this is Q dot equal to Ig minus Ix divided by Iy PR plus M by Iy. And R dot equal to, can write Ix minus Iy divided by Ig PQ plus N divided by Ig. And this is, you can say, this is the rotational dynamics. So if you notice here carefully, we have the coupling terms. So here we can say these are the terms are kinematic coupling. These are the terms basically we can write here, kinematic. And also we have the coupling terms here also, if you notice carefully here. We have QR, P, PR, PQ. So these are, we can sometimes refer as the these are the personal. So here also we have these terms, we can sine theta, cos theta. So these are the terms also exist in the system, and this is also making the system nonlinear. So if you look, this equation is highly nonlinear. So that's why it is very preferable to design a nonlinear control for this original dynamics. But if you are starting the linear system or linear control synthesis, so if you apply the small partition theory, we generally ignore these terms, these coupling terms we ignore, and we are making the system very simplified form. So that is not maybe sometimes not feasible if the system demands high accuracy in the system. So to avoid this kind of problems, we generally study the nonlinear controls for the nonlinear system, where the accuracy is very important and demanding for the comfortness of the passenger if you consider the aircraft system, passenger aircraft system. Now, let's look how we can come up some closed form of the nonlinear system equations. So, system in closed form. So let's assume we have the first OD of the nonlinear system defined as x1 dot equal to f1 x, or you can write time also dependent, t x1 x2 dot xn, and we have multiple input in the system u1 u2 dot u3, and x2 dot equal to f2. So this f1, f2 are the nonlinear functions in the system. So you can write t x1 x2 dot xn u1 u2 u3. And we have the, let's say in the last equation in first OD form, xn dot equal to fn t x1 x2 x. Let's define, this is equation number, where we can, where basically we can say where x1 x2 and xn, these are basically state variables, and u1 u2 un is the control inputs in the system. Okay. And if you write these states in vector forms or matrix form, we can write let x equal to x1, x2, xn, and u is the control input, which is u1, u2, un. And the nonlinear function f, let's define this as t, x, and u. So this can be defined as f1, f1t x u, f2t x u, and dot fn t x and u. So this is the nonlinear functions. So now if we write in compact form, we can write the above terms in this form: x dot equal to f of t, x, and u. This is we call in nonlinear system, sometimes we define as state equation. And output equation also you can define as h, t, x, and u. This is we call output equation. So these are the terminology we'll be using while we'll be studying the control synthesis system. Now, with the system does not explicitly depends on the control input. So these are the very important points, please remember. When the system that does not depends explicitly on control input, or we can write this is, let's assume this is the equation number. Equation 2 can be written as x dot equal to f of t into x, sorry, t comma x. So here the system does not depend on the external inputs or the perturbation input, anything. And let's just define this equation number 3. Once this condition happened, and if the system can be written in this form, we call unforced system. This is does not affected by any external force or torque, then you can say there is the unforced system. Unforced system. And another condition, when an unforced system is independent of time, it means x dot equal to f of x. And this, when we have this kind of system, what we call time invariant system. Invariant system. This is very, very important. So we say that the system, since the system does not depend on time, the system also we can call autonomous system. The system is autonomous. If dependent on time, then you can say system is non-autonomous. So these are the definitions very important while discussion of the control nonlinear system. Now we'll go to some important part based on this equilibrium point, because this is the one of the most important point in starting the nonlinear system. Equilibrium point. The equilibrium point, a point said to be equilibrium if it has property that whenever the state of the system x starts at the equilibrium point and it will remain at that point. So I can write here a point. This part we already discussed in the last first course, Introduction to Aircraft Control System, but still I am repeating this thing because these things are very important for studying the nonlinear systems. A point x star, for example, this is the equilibrium point, is said to be an equilibrium point if it has property that whenever the state of the system so we can say the current state x starts at x star, it will remain at x star. for all future time. This is basically desirable property when designing and implementing a control system. This is very, very important. This is the desirable property or property when designing and implementing a control system. So let us consider we have the non-autonomous system. Let us consider, let us consider we have autonomous system. Let us consider the system x dot equal to f of xt. For example, this system, the point x equal to x star is an equilibrium point at time t equal to t naught if the following condition hold. So at equilibrium point we can write x star. This equation should satisfy at the equilibrium point. So we can 0 for all t greater than t naught. So what does it mean? Because we have a system here. For example, we have the system x dot equal to f of xt. So to find equilibrium point, we'll put this equal to 0. Why? Because equilibrium point at some point where there's some constant value, right? So at that point, dx dt we can assume to be 0. And if we satisfy this condition at equilibrium point, so this equal to also 0. So if you solve this equation, we'll get some x terms, and these are basically equilibrium point. And here in this definition, we are defining that x as the x star equilibrium point, which will satisfy this condition. And so this is for the non-autonomous system. But if it is autonomous system, we can say, so if it is autonomous system, the condition for an equilibrium point becomes independent of the initial time t naught. So we can write f of that is we can write f of x star equal to 0. So this is how we can define at the equilibrium point the function is equals to 0. So here, if you consider if the equilibrium point not equal to 0, how will happen? So most of the cases we can write, let me write something that is very important. We consider or we shall only consider systems with equilibrium at the origin, which is x star equal to 0. This is the favorable condition for designing control system. It is, if you have the equilibrium point, this kind of condition, it will be easy to come up with the stability of the system. But if it is does not, the equilibrium point, if it is not 0, we can change the system to another domain where the equilibrium point will be 0. So let's look how we can do it. So for example, let us consider the following system. Where z dot equal to g is a function zt, for example. And let's assume the equilibrium point for this system not equal to 0. So let's equilibrium point. Let us define this is equation. For example, for equilibrium point of 4, we can write z equal to z star, some equilibrium point which is not equal to 0 at t equal to t0. Okay. So now let's consider, let us consider the change of variable, x equal to g minus g star. Okay, this is the condition we have to know. But one thing, don't forget, this is we are assuming to be constant, right? In that case, then we can write x dot equal to g dot equal to, we can write g in g is function of x plus z dot z star, which is t, we can write. So now defining f of xt equal to z x plus g star t, we can see that x dot equal to what? X dot we can write f of xt has the equilibrium point at x equal to 0, at t equal to 0, t naught, sorry, t equal to t naught. So this is how we can say that system has, if the system does not have the equilibrium point 0, we can make another system. We can come up with another system with the change of variable, and where we can come up for the new system, the equilibrium point can be 0. So this is how we can define the system, how we can define the equilibrium point of the system, and how we can come up the compact form of the system if there are multiple equations which are OD form, and how we can come up with this form. And for particular this form, how we can come up the different concept of unforced system, forced system, and what is the definition of the equilibrium point. And at the equilibrium point, the function solution goes to 0. And even the equilibrium point not equal to 0, how can make the new system where the equilibrium point will be 0? So this is how we can study the equilibrium point of nonlinear system. Let's stop it here. Next lecture we'll be studying the stability of the system. So how we can come up the system stability with considering the equilibrium point. That is very, very important for starting the controlled synthesis. Based on the control, we can come up so whether the system is global stability or asymptotic stability or other stability condition. We'll continue from the next lecture. Thank you.